Another gravity problem to look at, hopefully one that will help you guys with your homework that you guys have tonight. We have a planet that's been discovered. We know the mass of the star that it's going around, and we know how far the planet is approximately from the planet. By the way, this isn't a made-up planet. This is a real planet that they found, Kepler 78b, I think. Our goal is to find the orbital velocity, though. So for the orbital velocity, this is already starting to look like a gravity problem. But really what we always need to do is start our problems, if we're talking about some kind of object that's moving, the way that a planet does, would be with an acceleration expression. So from here, we have our Newton's second law. We know that there's going to be forces acting on it. We have the mass here that represents the mass of the planet, because that's who we care about. And we're going to try and find the acceleration of the planet. But since it's a planet that's going through an orbit, a circular orbit, we know that this is actually a centripetal acceleration. And we also know the only force acting on it is the force of gravity. So we can do two things. The first thing we can do is we can turn this into v squared over r, because that's a synonymous value for the acceleration if we know it's going through circular motion. We also know that the only force acting on it is the force of gravity. So we can substitute that in as well. And finally, divide by the mass of the planet. Okay, so that's a good step, but let's expand this term out a little bit more. This is a planet that's not on Earth, so we can't use the W equals mg, because this is it's not on Earth, it's not near Earth, it's a totally different star system, nowhere even on the surface of the planet. So we can't use that one. Instead, we're going to expand that formula out to our universal formula for gravitation. Gm1, have m1 be the mass of the star, and m2 be the mass of the planet, all over r squared. And then we can divide that by the mass of the planet. This is my force of gravity expression right there. And then my mass of the planet still needs to be on the bottom. Then we can just pull down the v squared over r. And from this step, there's several things that are going to cancel for us. We have a mass of the planet in the numerator and a mass of the planet in the denominator, so they'll cancel. And now that we did that, you can see that the radius of the planet is in the denominator on this side, and not the radius of the planet, but the distance, the radius of the orbit, so the distance between the planet and the star is in the denominator, and it's also in the denominator there. So I can cancel only one r. I can't cancel both of them, but I can get rid of that r and one of the r's that's there. So going to our next step, I'm going to change colors so we can hopefully keep this a little bit more organized looking. We find that the velocity is equal to g times the mass of the star all over r. And just as an aside, you could write it like this too. That's just as good. I mean, for that matter, you could write it as this times 1 over r. Like, those are all exactly the same thing. It's just your preference how you want to write it. So from that step, though, we're still trying to figure out what the orbital velocity is. We're trying to find orbital velocity. Why don't we square root both sides? So that's g over mass of the star, or g times mass of the star over the radius, orbital radius. Again, remember, it's not the radius of the star itself. It's the distance from the center, or the radius of the planet. It's the distance from the center of the star to the center of the planet. So be really careful with that r value, because even I've been messing up and calling it the radius nonstop. You need to really think of it as the separation. So from here, we can just plug in some values. We know that g is 6.67 times 10 to the negative 11th. That's on your formula sheet. The units are Newton meter squared over kilogram squared. Multiply that by the mass of the planet. The mass of the star is 1.61 times 10 to the 30th kilograms. And then we can divide that whole monster scientific notation beast by the radius, 1.33 times 10 to the 9th. Okay, so this is something you should plug into the calculator, and you should probably practice plugging it in to make sure that you get the same answer I do. But I pre-plugged it in so I could get it, and I got 2.83 times 10 to the 5th meters per second. And so that's our answer. Just as an aside, the speed of light is 3.0-ish times 10 to the 8th. So this is 1,000 times slower than the speed of light, but insanely fast for a planet. Like, we're approaching like it's close to speeds where time would actually be different on this planet than it would be on other planets in the solar system. So just an interesting fact. That's how you set that all up. I think really you need to focus on making sure you know how to yourself get to that step right there. Plugging in the values is going to be different for everything, but knowing how to go from here all the way to there is really something that you want to develop a skill